Hey guys, here's the spiral review for spiral 17. First up, we've got some rational exponent stuff. I'm going to multiply my two numbers in the first thing. I get negative 12 times 5 is negative 60. And then I'm going to add some exponents because I'm multiplying. So we've got negative 2 fifths. And to that, we're going to add 2 sevenths. I'm going to make those get some common denominators. So I've got 7 over 7, 5 over 5. And next level down. So we've got negative 14 over 35, negative 14 over 35, plus, wow, it's an awful 35. 10 over 35 is negative 4 over 35. And to make that positive, we're going to make this 1 over that. Cool. Now let's look at the y's. So we're going to start off with y, negative 3/4 plus 5/7. Going to multiply this by 7 over 7, this one by 4 over 4, and I end up getting negative 21 over 28. And here I'm going to have positive 20 over 28. That'd be y to the negative 1 over 28. To make it positive, I'm going to put that under 1 rather, and I get a final answer of negative 60 times 1 over x to the 4 35ths times 1 over y to the 1 over 28. Next up, we've got 256, x to the 4th, y to the negative 5/2, all raised to the negative 1/2. First thing I'm going to do is distribute that exponent to all pieces of this. So we get 256 to the negative 1/2, x to the 4 times negative 1/2, and y to the negative 5/2 times negative 1/2. And if you continue with that, I can write this negative 1/2 is the same as 1 over positive 1/2, and a positive 1/2 is the same as the square root of something, so it's 1 over 256. 4 times negative 1/2 is going to be x to the negative 2, which I can rewrite as 1 over x to the positive 2. And then we got y 5/2 times negative 1/2 is going to be negative 5/4, which I could rewrite as 1 over positive 5/4. So in looking at this, square root of 256 is 16. We get 1 over 16, so 16 is in the bottom. We've got 1 over x to the plus 2, so that's x squared in the bottom. And y to the 5/4 on the bottom with a 1 on top. 1 is 1 times 1 times 1 is 1. Cool. Writing in radical form, I'm going to set up my radical. I know the stuff on the inside goes on the inside. The denominator becomes the index, and the numerator becomes the power. Converting to exponential, we're going the opposite direction. We've got 42z, and that's going to be to the 12/5. Simplify. First thing we do is start what I did up top and distribute that to both pieces. I get 400 to the negative 3 over 2, and negative 6 times negative 3 over 2 is going to be positive 9, so that's x to the 9. Okay, next step, I'm going to convert this part, my first part, into a radical. And that means I'm going to do the square root of 400 to the negative 3. I like keeping the negative with the exponent. It makes my life a little bit easier. X to the 9th. Square root of 400 is 20. 20 to the negative 3, that's going to be a big number. It's going to be 1 over 20 to the 3. 20 times 20 is 400, times another 20 is 8,000. Woof! Next up, 125 to the 1/3 times x to the 6th to the 1/3, which is going to be x squared. 125 is to the 1/3 is the cube root of 125, x squared. Cube root of 125 is 5. 5x squared is our answer. Moving ever onward, we've got function operations and inverses. I've got some functions defined up above, and I've got to find f of 4 minus g of 2. That means I'm going to plug in 4 for f, so we've got 2 times 4 is 8 plus 3 is 11. And from that we're subtracting, plugging in 2 into g, so that's going to be 2 times 2 minus 2 all squared. So that's going to be 4. 11 minus 4 is 7. We've got f of negative 2 times g of 3. So we're looking at 2 times negative 2 plus 3 multiplied by 2 times 3 minus 2 squared. 2 times 3 is 6 minus 2 is going to be 4. 4 squared is 16. 2 times negative 2 is negative 4 plus 3 is negative 1. Negative 1 times 16 is negative 16. Next up we've got f of g of 2. First I'm going to find g of 2. And, oh, I did that in the first one. That's going to be 2 times 2 minus 2 all squared. In other words, 4. And I'm going to take that and find f of that. So f of g of 2, we just found g of 2, is the same thing as f of 4. And f of 4, hey, we did that in the first problem too. We found was 11. f of negative 2. First I'm going to find f of negative 2. And we've got 2 times negative 2 minus 3. Hey, we did that right above that. Huh. I wonder if that's a useful thing for us. We get negative 1. So f of negative 2 is the same thing as f of negative 1. And if I plug that in, I get 2 times negative 1 plus 3. Negative 2 plus 3 is equal to 1. All right, I've got to fill in a table for an inverse, and Mr. Butterworth told me that one of these is in the wrong spot. And the one of them that is in the wrong spot, I'm going to say is the 2. We're going to put that there for now and pretend that it never was there just to make our lives easier. We know inverses flip their x's and y's, and that means that my x's in my first one are going to become y's in the second one. So that's going to become 1 and 2. Negative 7 goes where my x is, and my 5 goes over there. 4 and negative 8 go on my other table. For the last part on this page, we're going to, given one curve, sketch the inverse of the curve. Okay, 0, 3 is going to become 3, 0. 3, 0 is going to become 0, 3. That's kind of awkward. I know this is my vertex because that's where the point was originally, so I'm going to just kind of draw that there. In fact, I might as well go through those two because those two connect. And then 6, 3 is going to become 3, 6. So there's 3, 2, 4, 6. And if I just kind of look at my line there, that's believable that that's kind of symmetric over that line. I'm going to turn this sideways just to make sure that if I were to fold this in half, we would get something that folds over itself, and that looks like it's the case. Zoom in just to make sure, and just because I can, because zooming is fun. Next up, we've got to sketch a graph of each function and fill in a table of values. I know the point that I'm going to choose to start with for a square root is going to be negative 2, because that makes the inside of the 0. If I plug in negative 2, I get 1 as my output. I'm probably going to go up 1 from there, because it's nice if I could make the inside of this a perfect square. So negative 1 plus 2 is going to be 1. The square root of 1 is 1. 1 times negative a third is going to be negative a third. Negative a third plus 1 is going to be 2 thirds. Oh, good. We're dealing with some lovely fractions here. My next nice number is going to be trying to get the inside to be 4, because the square root of 4 is 2. I know 2 plus 2 is 4, so if I make that a 2, that should work out. 2 plus 2 is 4. Square root of 4 is 2. Negative a third times 2 is negative 2 thirds, plus 1 is going to be positive 1 third. And finally, it would be really nice if we could make this the next perfect square, which is 9. And to get to 9, square root of 9 is going to be 3, but that's got to make it 7 on the inside. 7 plus 2 is 9. The square root of 9 is 3. Negative a third times 3 is negative 1. And negative 1 plus 1 is 0. Let's add some points in. On the vertical, I'm going to use each of these just so we can see this nice and clearly. Is going to be 1/3. So every 3 lines is going to be 1. That'll make it a little bit easier for us to graph. I'm also going to zoom way in so we can see this a little bit better. Okay, negative 2 comma 1, so negative 2. That's my end point. Negative 1 comma 2/3. 2 comma 1/3. 2, and then 7 comma 0, 3, 4, 5, 6, 7. Okay, very carefully, I'm going to draw my curve, totally missing that middle point. There we go, it's so much better. And thinking about the domain, we're starting at an x value of negative 2. And from there, we're going to the right, so this is x is greater than or equal to negative 2. For the range, we're starting at a y value of positive 1. And that's my highest y value. My graph then goes down from there. So x is less than or equal to 1. For our next one, we've got a cube root. This one I'm going to start in the middle of my points. And I'm going to choose, again, whatever makes the inside 0. We talked about this as something called an inflection point. It's the point where a curve kind of balances and flips on itself here. And here we've got negative 1. And if I plug that in, I get 0. 0 minus 2 is negative 2. I'd love to try to get the inside of this to some nice clean numbers. Let's try to get to positive 1 and negative 1. And since I've only got a few spaces, maybe we could try to get to positive and negative 8, which are also perfect cubes. Looking at this, to get to positive 1, I've got to make my x 0, because 0 plus 1 is 1. To get to negative 1, we're going to make this negative 2, because negative 2 plus 1 is negative 2. To get to 8, I'm going to make the inside 7, because 7 plus 1 is 8. And to get to negative 8, I'm going to make this negative 9, because negative 9 plus 1 is negative 8. When I plug these things in, let's see what happens. All right, 0, cube root of 1 is 1. Negative 2 minus 2 is negative 4. 7, cube root of 8 is going to be 2. Negative 4 minus 2 more is going to be negative 6. Negative 2 makes negative 1. Positive 2 is going to be 0. Negative 9 plus 1 is negative 8. Cube root of negative 8 is negative 2. Negative 2 times negative 2 is positive 4. Minus 2 is positive 2. Oof. Plugging those points in, we've got negative 2, 0. We've got negative 1, negative 2. We've got negative 9, positive 2. We've got 0, comma, negative 4. And we've got 7, comma, negative 6. And this should make for us a nice graph that looks something like this. The domain for all cube root graphs is going to be all real numbers. And if you want to be fancy with your notation, we use a double-barred R to represent all real numbers. The range is going to be similarly all real numbers. And again, if you wanted to get fancy with that, you could use a double-barred R to represent all real numbers. We've got to solve an equation involving a radical. Here we've got 2 plus the square root of 5x minus 3 is equal to 4. And first thing I've got to do is to get my radical piece by itself. So this part I'm trying to get by itself. Minus 2 to both sides. I get the square root of 5x minus 3 is equal to 2. To get rid of a square root, I'm going to square both sides. And that takes me to 5x minus 3 is equal to 4. plus 3, 5x is equal to 7, x is equal to 7/5. Moving on to the other side. Again, this is the thing I'm trying to get by itself, so we're going to divide both sides by -3. I get the cube root of 2 minus 5x is equal to -6. To get rid of a cube root, I'm going to cube both sides. I get -216 is equal to 2 minus 5x minus 2 minus 2. -5x is equal to -218. Divide by -5. I get x is equal to 218 over 5. And lastly, we've got graphing a rational function. We've got to identify some important features of this graph. And I might start off by finding an x-intercept. X-intercept happens when my numerator is equal to 0, so -5x plus 15 is equal to 0. Minus 15 to both sides, divided by -5, I get x is equal to +3. Okay, let's draw that in 1, 2, 3. I'm going to find a y-intercept. A y-intercept happens when I plug in 0 for x. So we get -5 times 0 plus 15, and 0 minus 5 is equal to -3. Vertical asymptote happens when the denominator is equal to 0. I'm going to write denominator equals 0, numerator equals 0, x equals 0 for those guys, which means that x equals 5. I did not leave enough room to make this a happy graph. And then in looking at the last piece, horizontal asymptote, I'm going to plug in some really big numbers. And if I plug in, I don't know, 1,000, I get -5 times 1,000 plus 15 over 1,000 minus 5. So that's going to be -4,085 over 4,985, which is pretty much -5. As an alternative, if you take a look at the x terms, noticing that they're of the same degree, you can kind of just divide them to get what happens at the end. So -5 divided by -5x divided by x is going to be -5. And again, didn't leave much room. My horizontal asymptote would be down here. I know I've got to go through these 2 points, and that's going to make an asymptote out of me when I hit those points. See what I did there? And then I'm going to zoom out so I can actually draw the other half of this graph. We should have another half of this graph down here. Again, following these 2 asymptotes, so that we never actually reach them. We're approaching those values. We should have a graph that comes in pretty comfortably like this.